So let's look at an example of how we can do calculations involving titrations. So this is an example from your textbook, and it's how can we measure calcium in urine. So this is a kind of fun example. And so this is a 3-step process that's given in the textbook. It says step 1, precipitate calcium from the solution, the urine solution, with oxalate. So oxalate is the C2O42 minus ion. So the calcium turns into a solid and we form calcium oxalate. All right, so we get the precipitate. We wash that with ice cold water to remove any excess oxalate, and then dissolve the solid in acid to obtain calcium and oxalic acid in solution. So all of our oxalate that's present turns into oxalic acid. And then what we're going to analyze is actually the oxalate. So we're going to titrate oxalate with permanganate, and that's standardized, and it'll reach an endpoint that's purple, and that's what we see. So the first step of this is that we need to standardize our permanganate solution. So suppose that we have a nice primary standard of sodium oxalate, and we have 0.3562 grams, so listed here, of our sodium oxalate dissolved in a 250 milliliter volumetric flask. If we take 10 milliliters of that solution and it requires 48.36 milliliters of potassium permanganate for titration, what is the molarity of the permanganate solution? Okay, so how are we going to approach this? Well, step 1, we need to know what's the concentration of the oxalate that's participating in this reaction. So we know we have 0.3562 grams of sodium oxalate, and we need to convert that to moles of oxalate. And once we know the moles, we can divide that by the volume that it's in, 250 milliliters, and figure out the concentration there. Okay, so we're going to need the molar mass of sodium oxalate. I'll go ahead and just delete this here. So this is a solution here. We'll go through this step by step. So the molar mass is here, and you can double check the work here. 134 grams per mole. So we need to take this 0.3562 grams times 134 grams per mole. And we can take all of that divided by 250 milliliters. All right, and we should have 4 significant figures in our answer here. And that gives us the 0.01063, carry an extra 3, molar solution. So this is the concentration of our standard oxalate. And we know if we take 10 milliliters of that, all right, 10 milliliters of oxalate, as it says here, the moles of oxalate in 10 milliliters are, we take our molarity, moles per liter, times our volume. That tells us we have 1/10 of that amount. So it's 1.0633 times 10 to the minus 4 moles. Or we can write that as millimoles. This is a unit that's pretty useful in analytical chemistry and titrations especially. Now we need to take the stoichiometry into account. So we know that for every 5 moles of oxalate, it will react with 2 moles of permanganate. So our moles of permanganate will have 2 moles, as it's showing here. 2 moles of permanganate for every 5 moles of oxalate, so we need 2/5 times the moles of oxalate that we have. So we can plug in this value here, and that gives us 0.04253 millimoles of permanganate. So then to find the concentration of the permanganate in our standard, we take the millimoles here, divided by the volume. So it required 48.36 milliliters. So we take our moles over our liters, and that gives us our concentration here. So remember, the final goal that we're trying to find here is what was the concentration of the permanganate that we used to react with our known amount of oxalate. And so that tells us that the concentration of our permanganate is 8.7947. That last digit is not significant anymore, but we carry it through just to make sure we don't have any rounding errors, times 10 to the minus 4 molar.